Hi, I'm Chase Mullen.
Hi, I'm Patrick Bronner.
My name is Jamie Curtis.
Hi, I'm Shannon Bradley.
The power industry has a myriad of fault sensing technology within their transmission and distribution networks. However, most utilities do not possess the ability to autonomously perform analysis on the data. Utility companies are typically left feeling alone in a silo of their own data that they don't have centralized tools to make sense of. The Distributed Grid Anomaly Detection project aims to help utilities make sense of their data silos and to learn from other utilities' experiences in a secure and near real-time manner. The solution begins with an application-specific proof-of-concept field device that detects fault information from intelligent electronic devices in the field and runs the information through our machine learning algorithm to detect the nature of the fault. This device then securely checks in to the central office server to deliver the fault and its detected fault type for protection, automation, and reliability engineers to consume on a 3D map that has a grid overlay containing the utility company's grid layout and a heat map with contextual data regarding the type of faults that are happening and where they are happening at. If this fault does not fit into a classification that has been seen before, it is indicated for the utility company's engineers to be investigated. The fault did not cause a breaker to operate, but was identified with high confidence as being a fault on phase A to ground, most likely due to intermittent tree interference. The utility schedules its vegetation management truck to include that site in its schedule the following day and cuts down the obstruction, preventing the possibility of a fire or an outage in that area. As you can tell, this is an ambitious project. The team is currently focusing on the ability of the central office software to indicate the location of the fault on a 3D map and to classify the fault using machine learning by using a large amount of data that we receive from utilities to train the machine learning system. If the development of this central platform goes as planned and finishes early, we hope to then move on to the development of the custom field device and the cloud platform as time allows.
Mentor selection was important to us. We wanted to go with someone that both had experience outside academia and had the education to back it up. We eventually chose Michael Starkey as our mentor. He is a power systems researcher at Oak Ridge National Lab.
Now, to speak a little on data acquisition. Our team had a lot of initial difficulty getting any fault data. We contacted 20 plus companies and worked within our own companies to get access to any sort of fault data that we can analyze. We've had some recent success in the last 2 weeks where we've received our first sets of fault data, and we're poised to retrieve many more in the upcoming month so we can begin methods to compile and analyze these data sets.
It was apparent after the initial planning phase that our scope would need to be clarified and simplified to avoid overreaching. After considerable debate between the group, we decided to remove the real-time input requirement so that we could better focus on the analysis portion of the project. We also decided that adding real-time analysis and cloud fault storage could be stretch goals if we complete the main portion of the project with time remaining.
While we have not received a plethora of data, we do intend to sift through the data that we have received and group like faults together. This will allow for easier training of our algorithms.
We plan to continue learning about MATLab's machine learning capabilities as well as other platforms. Ideally, we would like for our AI to learn to identify typical fault types, be it line to line, line to ground, through phase balance.
Now, on to the competition. We researched a similar technology called distribution fault anticipation. It was originally to prevent wildfires in Texas. After several years, they've increased their scope to output location and equipment failure. They have had several successful case studies at this time, and we will be looking into their product a little more thoroughly throughout the semester. One thing they do that we don't plan on doing is they are installing their own hardware on poles to monitor the circuit and give better visibility into the circuit. We want to move away from that.